Hello, welcome to the second part of analysis of variance. In the first part, we saw what variance is, and I explained what the F distribution, an important distribution underlying the analysis of variance, is. What we'll do now is have a look at what the analysis of variance actually does when it interprets data, and we'll have a look at the major output of the analysis of variance, the so-called ANOVA table. And then finally, in the third part, we're going to be looking at the assumptions that the ANOVA makes. Ronald Fisher himself invented the analysis of variance, and he suggested that it's not really a mathematical theorem, but really a convenient method of arranging the arithmetic, as he said. Let's have a look at a really nice example. It's actually drawn from Graffin and Hale's excellent book of Modern Statistics for the Life Sciences. Here we have yields of wheat according to three types of fertilizer, A, B and C. And in each of these cases we've got yields from 10 separate plots. The first thing to do when confronted with data is, of course, to visualize it, and here is what the data actually looks like. So we have the yield per plot against the type of fertilizer used for each of the fertilizer treatments. We've got 10 observations. Now, eyeballing these data, it does sort of look like that fertilizer A provides the higher yield, and certainly there may be a difference between A and B. But of course this is being rather subjective, and what we really need is a formal analysis to actually test the null hypothesis that in fact at population level they are all the same in terms of the population means. How can we do this? Well, what we do in our mind's eye is look at the variability between the fertilizers in terms of the variability between the sample means, and then somehow take into account the variability within each of these groups. Now let's consider data of a rather different format, but the same general principle. Let's imagine that the yield in tons was around 9 for virtually all treatments in which we applied fertilizer A, and in treatments where we've applied fertilizer B, the mean might be around 5, and in those plots where fertilizer C was applied, it might be just over 1. In this case, it seems likely that there is pretty clear evidence of a difference in yield between those fertilizers, because the variability between the groups is very much higher than the variability within any of these groups. So simply by eyeballing these data and looking at how that variability is partitioned can tell us something about the likelihood of there being a treatment effect. Let's see this in another way. Let's have a look at these data here, under which we've got the yields with treatment A, B and C. Clearly there's relatively high variability in the data compared to the overall variability between those sample means here. So what that's saying is that it's quite possible that this difference here and here between the sample means has arisen by natural sampling variability overall rather than any individual effect of the fertilizer. So in this case, most of the variation in our data could be attributable to within groups rather than that between groups. Let's go back to our original data, where in this case we've got something of an in-between case where what we have here is some differences, it appears, between these sample means, but there's still relatively high variability within any individual group. So how much of that variation is explained by variation in group means, and how do we test for this? Well, what we do in the analysis of variance is that we come up with two estimates of the variance. One estimate is based on the average variance within these groups, and the other estimate is based on the variability between these groups. If the spread in the data as estimated from the variance between groups is higher than the spread in the data as estimated through the variance within groups, then what we might see is a departure of that ratio of the between group to within group variance from a normal F distribution, and this is what the analysis of variance is all about. So if the treatment has an effect, one would expect the between group variation to be higher than the within group variation. How can we partition variation in our data in such a neat way? Well, thankfully, there is a really neat way of thinking about variability in the data. It's not based on variance per se, but on sums of squares. Let me explain. Here is the grand mean yield over all of our data set. And the total sum of squares is simply the sum of squares of observations from that grand mean over all of the data set. It turns out that's a pretty good measure of the variability in our data set in terms of departures from that grand mean. And that's equal to the sum of squares of deviations of observations from their sample means for each of them all the way through, plus the sum of squares of observations group means from that grand mean. So for each observation it's got a group mean, and you sum and squared all of those individual sums of squares all the way through. So we can partition variability in this nice way. The total sum of squares will always be equal to the sum of squares within the groups plus the sum of squares between the groups. But it's very difficult to standardize a test based on sums of squares because of course it will depend on the amount of data that we have. If we've got lots of data, then any sum of squares is likely to be higher. So we can think about working out a sum of squares per available piece of data. This is where the concept of degrees of freedom comes in. I don't really have time to explain the concept in too much detail here, but it really deals with how many freely varying deviations do we actually have? How much information do we genuinely have when calculating that sums of squares? It turns out there's n-1 degrees of freedom when calculating that total sums of squares, because the grand mean will also be a parameter that's been estimated in calculating that sums of squares. So the genuine new information in that sums of squares is actually n-1. And for reasons which I won't go into, we have n-a degrees of freedom associated with the within group sums of squares. That's the total sample size minus the number of groups, where a is 3 in this case. And we have a-1 degrees of freedom associated with the between group sums of squares, where we're assuming that we know what those group means actually are, and a is 3, so a-1 is 2. It turns out that the amount of information behind each of those sums of squares, or sometimes thought of as a denominator in an estimate of the variance, are also neatly additive. Here's where the magic comes in. We can calculate the two estimates of variance that we're interested in based on the between group sums of squares divided by its respective degrees of freedom, and the within group sums of squares divided by its degrees of freedom. Here's one, and there is the other. And it turns out that if indeed the treatment has no effect, then those two estimates of population variance will be estimating the same thing, and so in effect what we would have typically is that distribution would follow an F distribution if the null hypothesis of the treatment having no effect were true. So this is what the analysis of variance does. First, it partitions the variability in the data in terms of sums of squares, and we now know that they're neatly additive. It partitions the variability in terms of the degrees of freedom, or the amount of information behind each of those sums of squares. Most importantly, it calculates various estimates of the population variance based on variability between groups and within groups. It then compares them formally using a calculated F ratio and compares that F statistic with an F distribution with the same number of degrees of freedom, in this case 2 and 27. So the significance here tells us the likelihood or the probability of us getting that test statistic, or a more extreme if the null hypothesis of there being no difference at population level were true.